SwayamPrabha. Digital India. Educated India.
In the last lecture of week 10, let us have a brief discussion about radiative heat transfer and how it is significant for hypersonic flows. We would look at its relevant in particular for hypersonic blunt body stagnation region. After that, we will look at some computational results on viscous and inviscid chemically reacting flow solution around a blunt body, and before we end, we discuss a little bit about astrophysical flows, a brief introduction. Radiative heat transfer effects. When do they become significant? That is the first question we would be interested to answer. So, when air gets heated to a very significantly high temperature of the order of about 10,000 Kelvin or more, radiative heat transfer effects become significantly important. The gas in general under such intense heating conditions can lose energy to its surroundings due to emission of radiation. Similarly, it can also gain energy because of the absorption of radiation from other neighboring fluid elements in a high temperature flow field. Because of the loss or gain of heat from or to a fluid element, the flow becomes non-adiabatic. In many of the flow problems of interest in compressible flows that we have been discussing till now, we have been making the assumption of adiabatic flow. However, that breaks down completely when we discuss about radiative heat transfer. Just to add to the information, radiation is energy emission in the form of electromagnetic waves or stream of photons. A radiative energy source, in this case a hot gas, emits a broadband spectral distribution with maximum energy content at a wavelength that is determined by the source temperature. We have a very simple picture over here. We will try to explain that. Before that, we go through the points written on the left. Radiative heating becomes an important component of surface heat transfer, where the Q vector would have contribution coming from conduction, diffusion and radiation. This we had introduced when we were discussing about the energy equation in the previous two lectures. Nature of the gas in terms of radiative gas dynamic interaction can be classified into two groups as follows. One is that it behaves like a transparent gas, in which case it emits, but it does not absorb radiation. The emitted radiation escapes to the surrounding gas. So, this is one possibility where it emits, but does not absorb. While in a self absorbing gas, it emits and absorbs radiation. The radiation emitted by the gas partly escapes to the surrounding gas and partly is self absorbed by itself. Now, keeping an eye on the general case of a self absorbing gas where both possibilities do exist, we look at a small element within a flow field where radiation emission, absorption, scattering, transmission, all these processes are going on simultaneously. There is some incident radiation that is coming in from this end of the element. It is transmitted through the other end, it is emitted, it is in scattered, out scattered as well as absorbed. So, there are a lot of phenomena that can be taking place simultaneously. Here through the incident and the transmitted part, we talk about a few terms which can explain the phenomena to some extent. If we have a small element of length ds here, the energy emitted is calculated using this expression J nu ds, where J nu happens to be the emission coefficient, nu is the frequency at which the emission is taking place, ds of course is the length of the element, the energy absorbed is k nu times I nu into ds. K nu happens to be the absorption coefficient, I nu happens to be the radiation intensity, and when we put the effects together we end up getting the radiative transfer equation, which is given by d ds of I nu equal to J nu minus K nu or kappa nu times I nu. When we recall the energy equation in one of its forms, where you recall that we had marked the dissipation function, we had mentioned it in the previous lecture, and this form of the energy equation involves the static enthalpy, then the divergence of Q can be represented in this form, where you include the conduction, diffusion and radiation all together, and then you try to expand on the radiation term over here and express them in the form of double integrals, where you have the frequency ranging from 0 to infinity and the solid angle to 4 pi, and then you try to integrate those effects and finally come to a form like this. E is the total energy emitted by the infinite slab of transparent gas, which we are modeling here with the basic concept that we already discussed in the previous slide. So, this is a radiating gas considered in the form of a slab of width or thickness delta and stretching to plus minus infinity in the y direction. So, if E is the total energy emitted by that slab of transparent gas in all directions per second per unit volume, it can be shown that E comes out to be 4 pi j. J of course is the total radiative emission per second per unit volume, and 4 pi happens to be the solid angle. It can be shown through some analysis that the radiative flux across the surface of the infinite slab will be given by the equation Q equal to E delta by 2. This is a very important result for us, because we can consider the highly heated gas behind a strong shock formed in front of a blunt body in a hypersonic flow field to be like that of a radiating slab of air. So, the above result is used to approximately represent the stagnation region radiative heating of a hypersonic blunt body. The stagnation point radiative heat transfer is then given by this expression, which we just saw in the previous slide. In this flow, we have a very large upstream Mach number. These are the properties of the free stream. These are the temperatures and densities immediately behind the bow shock. The shock standoff distance happens to be delta, which is like the thickness of the slab of air, and we are talking about QR stagnation, R standing of course for radiation, and we are interested with the stagnation region or stagnation point of the body. Now, the shock standoff distance, we had read earlier that it is nearly equal to r by rho s by rho infinity, where r is the radius of curvature of the blunt body at the stagnation point. Rho s by rho infinity of course is the ratio of densities across the shock, and then if you plug in the expression of delta into the QR expression, then you find that QR can be approximately represented by this expression, which is a very important one. Therefore, the transparent radiating shock layer would produce a heat transfer that is proportional to R, which is evident from this equation. This, however, is in direct contrast to the result that we discussed in connection with convective heating earlier, where we learned that the Q due to convective heating at the stagnation point of such a blunt body will be proportional to 1 by root over R. Therefore, radiative heating and convective heating give two different variations with R at the stagnation point of a blunt body. And since radiative heating is a very important consideration in the design of suborbital vehicles, especially in the nose region, where the temperatures are expected to reach about 10,000, 11,000 Kelvin. Therefore, radiation has to be given enormous importance. Therefore, the outcomes from the convective and radiative heat transfer expressions that we see here would have to be carefully considered. And there is often a compromise on the design of the nose radius, namely to reduce convective heating, a large value of R needs to be chosen, making it more blunt, while to reduce radiative heating, a small R needs to be chosen, which means the nose becomes sharper. Therefore, in all probability you would have to choose a R which is intermediate and experiment with it either numerically with some or with some wind tunnel testing, that what kind of heating is expected with the chosen R. This is a difficult design problem. With that, we just round off with a little bit of radiation heating effects in blunt body problems and move on to a little bit of simulation. This is a slide which we had a look at several weeks back, where we talked about the high to foam solver in open foam platform simulating Euler equations in the previous case, but now being used for 2D Navier-Stokes equations as well as Euler equations as separate cases. So, we would try to look at both inviscid as well as viscous results with 11 species model, where all the species are mentioned here, and with 20 equation model, that means 20 chemical reactions considered, and the details of the numerical scheme are provided here, where we discussed earlier also that different terms in the governing partial differential equations have to be treated with different approximation schemes. The convective terms, the viscous terms, the gradients are treated with different schemes of second or fourth order accuracy, which are either central or upwind. With strong advection effects, you have to use upwind schemes for the stability of the solver, and then with strong shocks and discontinuities, flux limiting has to be done in order to keep the solution stable and also clip off the oscillations which occur across strong changes. Vibrational and translational energy transfer handled with Landau-Teller equation, chemistry and molecular vibration tackled with the two temperature Park model, which we have discussed at length earlier, and the equations are time integrated using a second order accurate semi implicit Crank-Nicholson method. So, these are some of the details of the numerics, and we just take a while to look at what kind of geometry we are looking at. So, it is basically a circular cylindrical geometry. This is the flow domain which has been defined with the inlet coming from the free stream end. We have the body, the wall at one end, we have the outlet at the other, This is more like a symmetry boundary above and below which the geometry or the flow would behave identically in terms of a kind of a mirror imaging, and then different free stream conditions are defined over here: the free stream pressure, velocity, temperature, the mass fractions of nitrogen, oxygen, and the gradients of the different terms going to 0 at the outlet. At the wall, depending on whether it is an inviscid simulation or viscous, the major difference will come in the shear stress at the wall. So, when it is equal to 0, it stands for inviscid simulation, which means you are solving Euler. When it is greater than 0 and it is actually going to come out as a part of the solution itself, it is basically the Navier-Stokes solution that you are talking about. This flow essentially represents a free stream Mach number of about 19 with stagnation enthalpy of the order of 7.5 to 8 megajoules per kg Kelvin. And with these conditions, we expect chemically reacting flow, where the flow gets ionized. And if you were to look at the flow field by considering the overall temperature which exists, you may have a feature looking more like this. We will look at some of the specifics related to the chemical reactions. This is basically the forward reaction rate constant, where A is a pre-exponential factor. You can call it as the Arrhenius constant. Beta is the temperature exponent. Ta is the temperature of activation derived from the activation energy. That is what figures in the exponential term here. Tcf, that is another term which figures in the exponential part, is the controlling temperature of the forward reaction. And similarly, the reaction for the backward rate constant is over here, where the forward rate constant and the equilibrium constant gets involved, where the temperature Tcb is the controlling temperature of the backward reaction. Remember that non-equilibrium effects in terms of the chemistry can very well exist here, and in that case you have to account for the fact that Kf is often not the same as Kb, and one can be dominating over the other. There could be different kinds of variations. Essentially, the final outcome is that the net rates in the forward and backward directions would not balance each other, and the K equilibrium, its functional dependence on temperature is obtained from experiments. In this context, you need to recapitulate the Arrhenius equations which we learnt or discussed earlier. The nomenclature may be slightly different. The nomenclature that we are using over here is more well tuned with the flow solver which is used here, and we therefore are referring to this slightly different nomenclature, because you will see some of those terms figuring here in this slide, where you see the constant, the temperature of activation, the temperature exponent, and so on, and these are all from the high to foam solver. It is a 20 equations model. Some of the reactions are shown here, the dissociation or intermediate reactions that you can see over here. M is the third body or the collision partner, and details are available from the HTC reactions Earth 93 module of high to foam solver. If you move on, more intermediate reactions are reported over here. One of the important reactions that is marked over here is because you will see a plot related to NO plus in a few slides from now, and therefore it is particularly relevant for us. We will revisit these equations once again with more detailing of the governing equations in the context of the high to foam solver in a later lecture, which will come up in week 11 or week 12. For now, we are keeping the discussion abridged to some of the main points because of paucity of time. More intermediate reactions here, and then comes a a slide which is a little too populated, because we want to show many things together. And remember that there are a lot of recipes for your thought over here in this slide. So, rather than stating facts directly and trying to come to conclusions, I would leave some of these as open ended questions. So, we are trying to see a few things for which one of the plots that we see over here, which is marked as marked on the left, is basically a variation of properties along a line like this, starting from the shock front and reaching the body. So, you see it is a plot of NO plus the number density, which has been shown over here, and there is a sudden spike in the region where it encounters the shock and then approaches the body. We are following this line. So, that line essentially surfaces as the axis over here in the plot, and you can see that the sudden spike then comes down after a length. So, this is more like a relaxation length that you see in action, which you have learnt earlier in the context of non-equilibrium. Therefore, the sudden jump does not sustain, it actually reduces after a while, after things come to equilibrium. There is another plot where we have the variation shown along a line which is at 45 degrees from the horizontal, and we are trying to show the property variations away from the body towards the shock for this. So, you can understand that the shock lies somewhere here, while the body lies here in the one that we have on the right. So, this is the one we are following for the left, while this is the one that we are following for the right. Keeping this in mind, we look at some of the comments made, but again, as I said, that this gives you recipes for your own thought, because you have already come to the 10th week of the lectures, and now you already have good amount of knowledge base and some understanding, some judgment which you can apply to decide for yourself. The Euler solution does not show damping and recombination. We are commenting it in the context of the NO plus number densities that we see. While recombination reactions are noticed in Navier-Stokes, possibly the viscous damping in Navier-Stokes may be the reason. So, this is a question for you to explore. The spike seen near the wall could be due to the frozen nature of the flow, due to the rapid acceleration of the inviscid flow. Remember that the red colored one is Euler, while the green colored one is the viscous or Navier-Stokes simulation. So, the spikes, the oscillations are seen strongly both in the left as well as the right plot. The spike seen near the wall could be due to the frozen nature of the flow, due to rapid acceleration as the slip flow moves past the body. This is something you may recall we had discussed when we were discussing about inviscid flow past blunt bodies. The flow time scale is small. Additionally, due to rapid cooling, due to acceleration, the reaction rates would fall due to a decrease in pressure and temperature. The flow time within the boundary layer in Navier-Stokes simulation would be longer, and therefore, there is higher chance for the chemical reactions to occur at near equilibrium conditions. So, this is a comment made, but you have to judge whether this would make sense or not. You have to think, how do the tau f and tau c compare for viscous and inviscid flow over a blunt body? Which regions are expected to be in equilibrium, non-equilibrium or frozen in terms of chemical reactions? Because of paucity of space, I have used some abbreviations here. It essentially means equilibrium. Again, another fact that you have to keep in mind is that in viscous flow, the viscous dissipation in the boundary layer is a major factor. It is a source of heating. So, all put together, whether we can sum up the facts and try explaining these kind of distributions which we are getting through both viscous as well as inviscid solution of hypersonic flow over a blunt body is going to be a good exercise for you. You can similarly see the variations of translational temperature and vibrational temperature for the same simulations. Keep in mind that this is the left family of plots, these are the right family of plots, and you know exactly by now that how to interpret them, that in which locations have we made these plots. So, with that we move on to the last section of this last lecture of week 10. We would have a very brief introduction of astrophysical fluid dynamics, and there are a whole lot of extremely exciting phenomena which astrophysical flow dynamics or fluid dynamics contains. We will just try to have a brief glimpse of some of these cases through some more simulation results waiting in the remaining weeks of the course. Broadly speaking, there is a lot to study in this domain. There is star formation, galactic dynamics, where you could have regions of dense gases, you could have regions of largely dispersed particles, and there are different ways of handling them numerically. If it is a dense gas region, you may use techniques like finite volume or finite difference methods to handle them, which are abbreviated here as FVM and FDM respectively. And if it is broadly dispersed particle kind of situation, you may like to use particle based methods like direct simulation Monte Carlo, which is abbreviated as DSMC over here. Accretion disks which are formed around black holes, supernova remnants which are there in the case of a dying star, cosmological flows involving comets, stellar structures, fusion fission reactions inside a star, planets in our system, our solar system and beyond, and interstellar medium. So, it is a huge set of phenomena which are existing under the umbrella of astrophysical fluid dynamics. If you broadly try answering some of these questions like when will compressible hydrodynamics equations be satisfied in such flows, you have to essentially answer the question that have you tried comparing the mean molecular free path with the characteristic length scale of the phenomena. That is going to answer your question. So, the above comparison of relevant length scales decides whether we can consider the medium as a continuum or non-continuum, and therefore use techniques which are of the finite volume, finite difference kind, or particle based techniques and so on. And because of the extremely high enthalpy levels existing in astrophysical flows, they happen to represent some of the most extreme cases of compressible reacting flows. These are some extremely exciting pictures to get you charged up for this kind of a study, though it is quite challenging, but we will try to do some very basic review of the material. We have excitement in the form of star formation, galactic dynamics, accretion disks and supernova remnants represented through some of these extremely illustrative pictures taken from NASA and nature journal sites and so on. Broadly speaking, approaches to solve astrophysics problems can be particle based, as I already mentioned, where we take a Lagrangian approach to capture the interaction of many particles and their nonlinear dynamics in order to understand stellar kinematics, plasma jet sheet from neutrino stars, planet formation involving many scales in galaxies, while the regular fluid dynamic methods based on Eulerian techniques could be applicable where molecular mean free path is much lesser than the characteristic length scale of the problem, where we can discretize the compressible Navier-Stokes equations using finite difference or finite volume schemes, earlier abbreviated as FDM and FVM respectively in the previous slide, and continuum hypothesis is broadly satisfied in these kind of flows. This approach will help understand the formation of an underexpanded jet emanating from a star, an accretion disk formed around a black hole, the atmosphere of any planet, and so on. We would try to show you some results of these cases in a later lecture. To have a very brief view about the equations which are concerned, they look familiar, however, there would be more complications, more terms to model this kind of a phenomena domain. The momentum equation, for example, would contain Maxwell's stress tensor, where B is the magnetic field, I is the induction, and similar terms are going to show up in the energy equation too. You will have a magnetic flux conservation equation, and when you look at the total energy, you would also have energy contributed by the magnetic field in the form of Lorentz forces. Some of the references which may be very useful in reviewing this material, though it is not essential for you to spend a lot of time on these books, because the content of the course is going to spread well beyond this into other weeks of content, where you may not find so much time to spend on these books. You can do it later. Let us conclude by saying that in this lecture we had an introduction to radiative heat transfer, and we tried understanding the relevance in a hypersonic blunt body stagnation region. Some computational results on viscous and inviscid solution around a blunt body were discussed, and we ended by discussing about an introduction to astrophysical flows. Thank you.